this computer. Okay, so let's activate first the GammaPy environment. You can use Honda or Mamba, or maybe you have actually installed GammaPy in your base environment. Okay, Navanis has a question why VODF is needed when GADF is already there, because GADF didn't have a formal structure, let's say. And since the project is now, so it was really contributed for by the community and didn't have a release schedule, for example. The way of discussing was also not super smooth at times because everyone can intervene in the discussion. So the idea was really to have some more formal structure to, yeah, basically to make it more organized and also to make it last longer. That's basically the issue. So there is a committee now that runs the specification, that takes care of the specification, of verifying them, of verifying when new ones are introduced. Okay. Okay, back to the tutorial. Let's go to the repository where we have the notebooks, Acme Magic Codas, and let's open the notebook. Let's start with the first one, data exploration and significance estimation. Can you read the screen, or do I have to make it larger? Better like this?
Yes, this is better.
Okay, perfect. Okay, remember to select the kernel with GammaPy. I think I have it already. So in this first tutorial, basically, we will consider the brightest steady source in the gamma ray sky, the Crab Nebula. And so since it has this property, so it's the brightest source whose flux doesn't changes, with a small exception at high energies, let's say, it's considered as a reference source. So if you were to build your own very high energy telescopes, to be sure that you have built the telescope correctly, the first thing that you would do is to measure the flux of the Crab Nebula. Okay, so we will explore the data, we will see what's inside them, and then we will try also to try to detect the source and get a handle of how we do this process of estimating the significance of the signal. So to read the data, GammaPy has a data store class that basically can read at once all the data in a directory, and I'm pointing it to the Acme Magic Codas data Crab Nebula. So I want to read all the Crab Nebula data. And then we get the observation with this get observation function. What are the observation? The observation is basically the equivalent in the memory of the DL3 file. Okay, if you do dir observation, for example, this is a list of observations. So let's take the first one. You will see that it has basically all the properties of the single DL3 files. For example, it has a list of events. I think I show it later. Yes, let's go. So let's go in order with the tutorial. The first component is a list of events, okay? And as you can see, we have the physical quantities that are most important to do gamma ray astronomy. The coordinates, right ascension and declination, the energy, because we want to measure spectrum, and the time, in case we want to study, for example, how the flux of the source changes in time, if we want to find if there is some periodicity, if we want to find if there is some pulsed signal, okay? So each column is an astropy quantity. Maybe you know this class of astropy. It's fantastic because it allows you directly to handle units automatically. Okay, so the values carry explicit physical units. So let's start to histogram this data, no? To get a handle of what it is in the data. So the first thing that I do is a histogram of the energies. Okay. So this is a log-log representation. What kind of shape is this, more or less? Let's focus on the part above 100 GeV. What kind of shape is this? If you had to guess, does it remember anything from the presentations? looks like a power law of events, no? It's more or less a straight line in a log log space, no? Because of course, yeah, the flux of gamma rays is a power law most of the time, and here we are in the range where the exposure is almost flat. Let's say our effective area is almost constant. Okay, and we will see later how this histogram of events versus energy will play an important role in the spectrum estimation. So we will have to separate the events. Now we just have an histogram of all the events together. Okay, the other components that we have in the event list is right ascension and declination. So let's try to make a 2D histogram of the coordinates, basically. Anything interesting that appears? Do you see any interesting feature in the data? Feel free to speak up, eh? No need to raise your hand. Any interesting feature in the data? Does it look like a smooth distribution? Yeah, I also brought it here. Basically, we can see that at these coordinates, very close to the coordinates of the Crab Nebula, there is a cluster of events, right? There are many more events detected around these coordinates. And what I do in the next cell is just I put the coordinates of the crab in the same map, and as you can see, in the same histogram. And as you can see, it's exactly on top of the spot. So possibly these cluster of events are photons from the Crab Nebula, right? How could we assess it? How could we estimate the significance of a signal? So there is some background, right? Because if we are observing a patch of the sky where the only source in is the Crab Nebula, then what is the rest of these events? Let's say, what do they correspond to? Do you have any idea, any suggestion? Well, if this cluster of events is really photons from the crab, what is the rest of events in the histogram? In this field of view, there is no other gamma ray source, okay? In these few degrees of the sky that MAGIC is observing, the only active gamma ray source to our knowledge is the Crab Nebula. So there is no other gamma ray emitter. So what are these other dots?
Just diffuse background.
Exactly. Is cosmic rays more than diffuse background? Is basically background, exactly. It's just cosmic rays that have been misidentified as gamma, okay? Because when we create the event list, we put inside everything that we think it's probable to be a gamma ray, right? But there is no basically, the way that we obtain that is through a classification algorithm. So as you know, when you classify something with an algorithm, there is no way to make a clear cut to establish, okay, below, above this cut, everything is one type of particle, everything is some type of other particles, right? So along with the gamma ray events, we have still a lot of events that are cosmic rays and that are misclassified as gamma, okay? But we have to get rid of those. Then another thing that I wanted you to observe is that basically the telescope is not pointing at the source. And what I propose in the following cell is to use gamma pi to make a map. This is not a map. This is just a histogram of the coordinates. And when you make a map, you have to account of the proper, let's say, projection, no? Because you are projecting, let's say, a sphere, the sky, over a flat surface, right? So let's use gamma pi to make this map. Basically, we use the WCS geom. We will examine this type of element later when we do the 3D analysis, but basically it defines the pinning in right ascension and declination. So we are producing basically a map of 4-degree width with pins 0.05 degree, okay, width. And then we just fill the map with the count map with the events, okay? So I also plot where the telescope is pointing. And as you can see here, we can see very clearly the crab, but the telescope is not pointing at the source. And this is what we commonly do in gamma ray astronomy. This is called wobble pointing. We do not point directly at the source, but we let the source be at a small offset from the pointing position. Why do we do that? Because basically, imagine that the source is at the center of your field of view. Imagine that you are pointing directly at the source. Basically, to estimate the background, you would need another observation of an empty sky, basically of a sky empty of gamma ray emitter. The important thing is that the response of the telescope changes as a function of the offset, okay? So the farthest you are from the center, the worse is the performance. So you cannot put the source in the center and then estimate the background from the border, let's say, because you don't have the same response. So what we do is we put the source at a certain offset. In most of the cases, it's 0.4 degree for magic. We will estimate the background from a similar position, okay? From another position with a similar offset. So what we do now is we define what we call on and off region, okay? So let's say now we want to see how many photons come from the Crab Nebula. We want to make an estimate. Okay, so I'll just say, okay, I'll count all the photons in these regions, and if I make this count from what I call the on region, what do I get? The photons from the crab plus the background, right? There is an amount of photons, a background that I'm still counting in this region. How can I subtract them? Well, I'll take another region with a similar response, where the response is similar with an identical offset, basically, and I count the background from there, and then I subtract the two. Okay, and that's what we do. Okay, I put a question, but I replied to it myself. Could you guess why we stated that the off region has to be symmetric to the on? It's just a matter of performance of the system, of camera acceptance. You get the same response at the same distance, okay? Okay, so we get 869 on and 388 off, okay? So well, we see that there is an excess of 400 something events, no? Is this significant? How can we estimate it? And basically, this is where the Lemma formula comes into play. Everything clear so far? Let's make a small break for questions. So I just make a 2D histogram, a map of the data. I take a region that encloses the source. But here I'm counting both the signal, the photons from the crab, and the background, right? Whatever other cosmic ray that has been classified as a gamma. How can I subtract it with another similar region at a similar offset so that I get the same response? And that's it. Basically, here I'm just counting background. Okay. So what is the Lemma formula? I think Giacomo already explained it in the video, but for those who didn't check the video or just for the sake of the tutorial, let's repeat it very quickly. Basically, we can basically represent the events in the on and off region with a Poisson statistics, right? And then we have a Poisson statistic for the on region and for the off region. And for the on region, what is the mean of this Poissonian? Well, the signal plus the background, right? Because there I'm counting both. And in the off region, the mean of the Poissonian is just the expected number of background counts. And then what we do is we modify this formula to take into account that maybe on and off regions don't have the same exposure, right? Maybe I want to estimate the background from more than one off region, okay? So basically what you do is you correct this formula by a factor that represents basically the ratio between the two exposures, okay? Exposures might mean both time or area, let's say. So in case you would be using 3 off regions, okay, 2 more off regions, then in that case, I don't know if I can plot it directly with no. Then in that case, you would have 3 times the exposure in the off region, okay? So this alpha factor is just a correction. The likelihood to observe on and off event, certain number of on and certain number of off events, given these mean values, is basically the product of the two Poissonian distribution, no? And usually we use the -2, the log of this quantity, because instead of maximizing the probability, sometimes it's easier to minimize the log of the likelihood. And also because when you use the logarithm, all the product turns into sums, basically. So this is computationally easier. So yeah, basically what I do now is I represent this likelihood basically with the on and off. With first, I think I do it with an arbitrary number of on and off. So let's suppose we have found 20 on, 30 off, and a factor of alpha 1/3. So meaning, for example, we used 3 off region. Then I think I do here a simple plot of the likelihood. So this likelihood is a function of two parameters, no? G and B, right? Because it's the probability to observe a given number of on and off counts given a certain predicted number of, a certain expected number of signal and count. And what I wanted to show you is that when we consider the B parameter, the minimum of the log likelihood is at 30, which is actually our estimation of the background. Sorry, there is a typo here. And the on is at 20. So the minimum, the value of G that minimizes the likelihood is at basically 10. What is this 10? Well, basically is the on minus alpha and off, right? Is the signal that we counted in the on region minus the number of signal that we counted in the off region scaled with the appropriate scale factor, okay? Everything clear so far? So a good estimate of the excess, for example, might be directly to subtract the on and alpha, the number of off, okay? And then the next step is to do this likelihood ratio test, no? Basically, when you do a likelihood ratio test, you compare, you basically select a null hypothesis, in this case that there is no signal at all, against the alternative hypothesis, no? H1 that actually G is different than 0. So that actually in the on region, there is some signal, right? This G parameter is not 0. And this is basically the lemma formula, and it's also available in gamma pi. And once you get this quantity, basically this quantity, this likelihood ratio test, is distributed as a chi-square with 1 degree of freedom, according to the Wilks theorem. So basically, you can translate the probability corresponding to the output of this likelihood ratio test in units of standard deviation of a normal distribution, okay? So you get a number from here, and you can directly say how many units of standard deviation of a normal distribution it is. In particular, you just have to take the square root. Okay, so let's use our, let's say the hypothetical number that we were using, 20 on, 30 off, a factor of 1/3, a scaling factor of 1/3, because we used 3 of the regions. Basically, the likelihood ratio test gives us 5.41, and if we take the square root, we get 2.33 sigma, okay? So we see that in this hypothetical case, we do not have evidence to reject the null hypothesis, okay? No signal. Usually the threshold that we use is 5 sigma, okay? But in this case, we cannot claim basically that there is a significant signal. But what happens with the actual number that we find in our Crab Nebula observation? I remember that just by taking one on and one off region, we got 869 and on and 388 off. So let's plug these numbers. So we have a likelihood ratio test of 188. And then if we pass to the square root, we have 13 sigma. So in that data set, just taking an on and off region, just with one observation, so just with that corresponds to 20 minutes of data taking, we already detect the crab with 13 sigma, with a significance corresponding to 13 standard deviations. Okay, so I really wanted to highlight a bit how we use the likelihood, and especially I wanted to highlight how bright is the crab. See that just with one observation with 20 minutes, we already got 13 sigma. So very strong evidence for the presence of signal. Any questions so far? These are concepts that were already explained in Giacomo's video. If you have any other question, let me know. Yes, please.
Yeah, maybe I have just a very random question. So for the choices of the on region and the geometry, basically, we saw that it's the source is usually zero point 0.4 degrees away from the center.
Mhm.
It's basically already chosen in the observation, I guess, and just like why these exact numbers, I was wondering. And same for the regions, it was, I don't remember exactly 2 degrees or the size of the circles basically.
Mhm. Mhm.
Just, I mean, there's probably no magic to it, but where do these numbers come from?
Very good question. So, as you said, basically you already answered. It's exactly in the observation. Let's change to another one. Where did I fill the events? I wanted to show you. Okay, for example, here we see that in this observation, it was a 0.4 with this offset angle, let's say. And then basically what we do is we change the position of the source. So you see it was bottom right first before, and now the source is top left, right?
Hmm.
And if we change the observation, the position will change to
Hmm.
another graph maybe has only two wobbling point. Yeah, exactly. So it changes from observation to observation. And the idea is that you want to sample different positions in the camera, let's say. Okay, so you want to place your source in different camera position at the same offset, and you want to do the same with your background estimation. So you want to estimate the signal in different position, and at the same time, you want to estimate the background from a similar position in the camera. So typically we do two or four wobble pointings, meaning that the offset is 0.4 typically, and then the angle changes between 2 and 4 positions. And typically, I think this is an offset in the declination angle, if I'm not wrong. Why 0.4? Because it's an optimal position, because basically the maximum of the response, the maximum of the acceptance will be at the center of the camera, because the camera is basically a set of pixels, no, that measure the development of the air shower, and the more the air shower are in the center, the better you can estimate them, right? So the air shower that hit the camera at the border, you have poor estimation with respect to those that hit the camera at the center, no? So typically you have the maximum of the performance at the center of the camera, and then it goes degrading when you go at higher offset. We will see it in one of the next tutorials. So 0.4 is some kind of optimal position where you still have good performance and you have enough space to basically to do the wobbling and to place different off regions. That's it. It's kind of a
Hmm.
optimal condition. As for the size, it's typically, well, you typically you should take something that is comparable with your PSF in general. It doesn't matter that much. And what we do and what we will see in the next analysis is that typically this size is optimized through Monte Carlo. Basically, what we do is, for example, we say, okay, the size of the on region is that which will contain 90% of events from the source or 75 events from the source, because we can actually simulate a point source and we can get how many photons will be contained within a certain region. So typically we choose a size that contains, let's say, 70 to 90% of all the photons from a point source, because in the Monte Carlo simulation, we are able to see how a point source will appear spread in our detector.
Right. Okay. Thank you.
Thank you. Okay, any more questions? Everything clear so far? Hopefully, yes. So to get an estimate of the signal, you can just do the on minus the off, corrected with the exposure. And then to get the significance, you have to do this likelihood ratio test, which is automatically implemented, let's say, in the Lemma formula and in the W stat count statistic of gamma pi. But another way to visualize basically the presence of a signal is to make a theta square histogram. What is a theta square histogram? So instead of counting all the events in the on region and all the events in the off region, let's do something different. Let's take the center of the on region, the center of the off region, and let's make a histogram of all the distances of the events from the center of these two regions, okay? So let's fix a point here and let's histogram all the distances of all the events. Let's take a point here at the center of off region and let's make a histogram of all the distances of all the events, okay? What would be obtained? This is basically what we do in section 1.3.3. Basically, I use AstroPy coordinates. So I take the center of the on region and I compute the distance, the separation of all the events coordinates. I take the center of the off region and then I take basically the distances from all the events as well. And then what I do is I will do an histogram of the square of these distances, okay? That's basically what is shown here. Okay, so we see the distances of all the events from the center, from the source, basically, the center of the on region is basically the source position, and the histogram of all the distances from the center of the background region. So I marked also in gray the theta square cut. So basically the size of the on and off region. So why do we have this feature here that we see that at the center of the on region, we have this increase of the events as we go close to the source. What is this showing us? Basically the presence of a signal, no? If I take the center of the off region, more or less, I have always the same number of events as I go far away from it, no? It's more or less flat. But if I take the center of the on region, which is the source position, the closer I get to the source position, the more events I get, right? And then on the right, I just made the difference of the two histograms. So you can see the excess counts. Okay, as you move towards the center of the on region, towards the position of the Crab Nebula, you see that the number of counts increases. So the question is, why the distance squared? I leave it as an open question and then you can reply whenever you want. Okay, so all clear so far? So different way of representing it. You are representing it basically in one dimension, putting the two coordinates together, considering the distance squared, instead of representing it on a map. And that's what we typically do to claim detection. We use this theta square method. And just to make a cross check, let's check that the counts that actually fall within this theta square cut, which is the size of the on region, and the counts that fall within the same cut for the off histogram are the same that we obtained before. And they are, right? 869 and 67. No, I think I messed up something. It should be, it was 400 something, no? 388 of counts. Sorry, it should be the same number. Maybe I made some mistake.
Yeah. Sorry, Cosimo, I think you made the observation number different. That's why.
Ah, okay, that's why. Okay, thank you. Yeah, right. I changed the observation number, so. So maybe I can fix it here. Thanks a lot. So events is observation was 0, right? Not the events. Observations. Yes, let's see now. No.
Was observation 0, so that should be correct.
Mm-hmm. Observations 0 for events. Okay. I don't know where the 388 was coming before.
I think the problem is that you changes the pointing coordinate. So yeah, the the Poynting holding.
Hmm.
The number 13, the box number 13, I think
Okay, I
when you
changed.
change it, yeah.
Okay. Sorry, you meant the cell 13 or?
The coordinate.
Of
It
the
might not
on and
look,
off.
yeah, it's
Okay.
box number 13, but
I see. I see. So maybe I changed the on and off region definition. Okay, but we got the same number, so that's what I wanted to show. Okay, so let's say this is a more visual way of showing the presence of the signal, let's say. But as you can see, what matters ultimately is just the number of on and off events. So I'll give you a couple of minutes to do this exercise. I would like you to create a theta square plot as we did before, but using all the observation, and then estimate what is the total significance of the signal. Okay, we did basically the example just using the events in observation 0, in the first observation in the list, but we have 98 of them. So take your time to try to do a histogram with all the observation. And yeah, feel free to ask any question. There are two ways, just to give you a suggestion, that you can go about it. You can either make a giant event list, basically, and one histogram, or you can make an histogram per each observation and then find a way to combine them. Okay. So choose the approach that you prefer. Let's see how we are doing with respect to the schedule. Okay. Okay, I think we're more or less on time. Did someone get the solution already? Might I ask? Okay, anyone would like to share their solution? Did someone get the histogram or you need more time? Any type of feedback is welcome. More time, please. Sure. Okay, I'll start to draft a solution. Did anyone get the histogram? I think we have to go ahead. Fernando got 172.62 sigma. And what approach did you follow, Fernando? Did you make a giant list of coordinates, or did you create separated a square histogram and then combine them? Try to stack the events of the event and follow the same procedure. Okay, perfect. Yeah, that was what I was trying to do as well. So I made a giant list with all the coordinates, which, as you can see, it's a million. And then what I was trying to do is compute basically that over all the Okay, Pavel as well, got 172. Oh, Gemini. Oh, come on. You use Gemini. Ah, from Stack. Nice, very nice. 199, that one got. No, it's a too big. Anyone wants to show their solution? I was trying to actually maybe that's the smartest way to go to let it stack the events because I made a giant list, but then when I try to compute a separation, it complains. Try to do is equivalent in frame, something that isn't a frame. But let's try just with two elements. Let's see. Okay. Then okay, it doesn't work on a list. If I convert the list to an array, no, it doesn't like it. So on offsets. So I can just loop, right? So separation from four, four, four. Let's see if I can get two lists. Of regions, enter for coordinate elements, coordinates. This should work. Okay, anyone else got the same result? So maybe the solution of Pavel is more efficient. Well, the solution of Pavel and Gemini, because it actually stacked the observation while I made a giant list of a million of events, and then I try to replicate basically the computation. And perhaps I should convert this to an array. Does anyone feel like sharing their solution or their plot? I mean, you can share your screen. Huh? Don't have to type in the chat if you feel like. Oh, okay. Not yet. Okay, thank you, Fernando. So basically, Fernando used you can see it in the chat. In the chat, he used the vstack function of AstroPy table, and then he just stacked all the events together. Yeah, I think that's more efficient than doing the loop with the list. Let's see. I'll just use Fernando trick. Very good. Yeah, much faster. And then I think here we'll go back to this. Events, all events, it's called now. Okay, 172. Center. Operation. I think I'm messing up something. Find the y limits of the theta square product. Thank you, Fernando. Right. Sorry, so stupid. Okay. Yeah, that's it. Thanks a lot. Okay, yeah, very good solution. Yeah. Theta square being minus region radius. Right. Okay, yeah, I get 172. Okay, very good. Any questions on this? Did everyone get the cumulative significance? Okay. Okay. Okay, very good. The second exercise, I leave it for you. The only suggestion that I will give you is that you can create a mask. So we have the list of all events that we created following Fernando's suggestions. So, for example, I think you can generate a mask. So if you try to write some logical relation, it should energy should produce automatically a mask. And then basically what you can do is apply to all the events. Okay, so we can call it events above 1 TD. We can basically apply this mask directly to the event list. Okay, because no, all events is already a table. Basically, all events is a table. It's another table. And basically, what you can do is you can directly apply this mask to the table, and then you can just use whatever you want. And as you can see, we went from 900,000 events, and when we apply the filter, we get 10,000 events only. Okay, so the idea is simply this. Then after you apply the mask, whenever you apply some logical relations, it will automatically produce a mask that you can apply to all the events. Okay? Basically the tip to solve the second exercise. Okay, so let's finish and then let's take a break. So the observation contain, let's say the observation of the gamma pipe class observation that corresponds to the DL3 file contain the events, no? And we can see that we can extract already quite a lot of information from the events, no? We can histogram the counts versus energy. We can create a map of the counts. We can even already establish the significance of the source. What if we want to go further? What if we want, for example, to estimate the flux of a source? So we need the IRF. What is the IRF? It's the instrument response function. And it's basically, it represents different, let's say, components of the response of the system. We typically have the effective area and the energy and direction estimators, the probability distribution of the energy and direction estimator. The probability distribution of the energy estimator is called regression matrix. We will take a look at it now. And then the probability distribution of the direction estimator is called PSF. And we will take a look at it tomorrow in the 3D analysis tutorial. So the effective area is basically an attribute of the observation. So we can do observation, just select one observation and do effective area dot plot. In general, the IRF are a function of the energy, of the true energy, and of the offset, let's say, of the distance from the camera center in Cherenkov telescopes, let's say from the center of the field of view. In this case, we see that we really don't have a dependency on the offset. Basically, we have a narrow range in offset, and the value is always the same. Can you imagine why is that? Why do we have basically only the response at 0.4 degree? Does this number ring a bell? It's basically this distance. What we know is basically that in our observation, the source will be sitting at 0.4 degree offset. So what is commonly done in Magic is to simulate the response only at 0.4 degree offset. Monte Carlo simulations are very computationally expensive. So basically we just compute the response at the offset where we expect the source to be. Okay, so basically all of our response is at 0.4 because the source will be sitting at that offset from the camera center. And when we want to study more than one source of the field of view, or when the source is not sitting at 0.4, as we shall see, we will use what we call multi-offset IRF, right? But for the time being, the source is 0.4, so I just need the response at 0.4 degree. And then basically, as you can see, for different, we really don't have any dependency on the offset. And then we can plot the migration matrix. I think this was explained in Giacomo's slides. Basically, what this represents is given a certain true energy on the x-axis, we have the probability distribution of its reconstructed energy. And the darker area will represent basically the most probable value at which the energy event with an energy in the spin will be reconstructed. And it's more or less diagonal. So let's say something with energy around 1 TeV will most probably reconstructed at 1 TeV, though as you can see, there is a certain spread, right? Okay, that's basically it. We shall see later in the next tutorial how these are useful. The last thing that I wanted you to do is to plot the histogram of the on and off events versus energy. Okay, so these are all the events in the on region and all the events in the off region, and histogram as a function of the energy. And we will see in the next tutorial how we will use basically these two distributions to basically to estimate the spectrum. Okay. Then I gave you the homework of making a similar histogram. Okay, so I will pause the recording now. And I think we can take a break. We are slightly behind schedule, but not so much. So let's say we reconvene at 11:15. Okay, so we have 20 minutes break. Is that okay? Okay, so see you in 20 minutes. Okay, so I think the break is over. We had an interesting discussion in the meanwhile in the chat. I don't know if you followed. So the result for the second exercise was 60 sigma when you filter all the events above 1 TeV. And then Carlo had a very interesting question about the theta square histogram because he asked, well, the number of events in the on histogram is significantly higher than in the off histogram. But when you go outside the source region, they should be the same, right? Because you are sampling the same number of events, let's say, no? And then what we saw is basically that the histogram actually go towards closer value the farther you go away from the source. I think the situation here is complicated by the fact that the crab is a very bright source. And Carlo actually says, I would have expected a peak in the Hoff histogram at 0.8 because that is the distance of the off from the crab, right? Right, but that's 0.8 squared because remember we are doing theta square histogram. So maybe this, yeah, the peak is, yeah, what we see around 0.6, right? Okay. Okay, yeah. Are there any final questions on this notebook before moving to the second one? I'm recording also, right? Yes. Any final question? Okay, then we can move to the second notebook where we will basically try to estimate a spectrum. What is a spectrum? It's basically, in astronomy in general, is some measurement as a function of the energy. Typically, it's the intensity of a source, and in this case, in our case, it's the flux as a function of energy. So we will do our normal import, then we load the observation again, and then let's reconnect to a question that actually Sarah made is how is the size of the on region determined? And I already gave an answer, right? In this case, what we can do is provide with the file the optimal size of the on region. If we know that we are going to perform an analysis like the one that we just performed using on and off region, what we can do is we can tune the size of the regions basically as a function of the energy. Why would we do that? Well, because basically the higher you go in energy, the more precise your direction reconstruction becomes. And you saw this basically in the theta squared histogram. No? When you start to filter with the energy, the distribution of the counts becomes much more peaked, right? So we can take smaller and smaller regions. No? And so what we have in each observation is basically this fratmax table that is basically an optimized theta squared cut or angular squared cut. Okay, and I compare here with the fixed cut that we used before. So we used some intermediate cut before, 0.2, but actually what we can do is take all the Monte Carlo events and we can select the cut that contains a certain fraction of events. I think in this case it was 75%. Okay, so we are sure that we have a region that contains most of the events produced by a point source because we can actually simulate how the spread of the photons, let's say how the detector will spread the photons from a point source. And yeah, basically we have that already in the files, right? So what we do now is we move from observation to a data set. If you remember the introduction to gamma pi, what we can do is one of the main functionalities of gamma pi is to move from the events to binnet data. No? So that's what we do now. We will go from observations to data sets. So basically we define the the source of interest because we want to extract on and off counts. We define two energy axes, estimated energy axis to make a histogram of our events, estimated energies because of the events that we measure that are in our event list. We just know our estimation of the energy, and an axis of true energies, the dependency that we have in the IRF to interpolate the response of the system. Okay. So we create a geometry which is basically a representation of the type of data that we want to use. We want to use, basically, we want to do 1D analysis. So we want to consider only the energy distribution of the events. So basically, the geometry that we are considered is basically 1 pixel with an energy array. It was illustrated here in this slide, okay? We want to do a 1D analysis. We are just interested in the counts versus energy. So what we are going to do is define a geometry which has only energy dependency, right? And no spatial dependency, or say a single pixel of spatial dependency. Then we have the dataset maker that will create the dataset, basically. So in this case, we can define the number of region that we want to find. And basically, the spectrum dataset maker will basically automatically generate the array of on and off counts, okay?
There was also a question in the chat, I think.
Yeah, sorry. Very good question. Why is the number of bins in the true axis? Is asking Guillermo. I'll reply in a minute, okay, Guillermo? Okay, let's see what the data reduction performed. Most of the objects in GammaPy have this peak function, which is very useful. So let's compare the first observation and the first data set, and let's see how the information has reduced. Okay, so we had here the effective area as a function of the offset, the migration matrix in principle also as a function of the offset, all the events that in this case for convenience are represented in a map, like we did in the previous notebook, and here the RAD max table. When we go to the data set, we see how the data have been reduced. So I have the effective area and the energy distribution only at my offset, 0.4, that the data reduction routine computed. Okay, my source is sitting at 0.4 offset, so I don't care about the response of the system in the rest of the offset. And it used also the energy binning in true energy that we gave it to the data reduction routine. I'll come back to that in a minute. And then instead of having all the bands as a function of coordinates, basically we have the counts in the on and in the 3 off regions. Okay, counts and background. It's basically the last histogram that we produced in the past, no, in the last notebook. Okay. So clear, so far so good. It's just basically an automatic reduction process. And now that we have the bin data, we can estimate the spectrum. So how do we estimate the spectrum? We use the forward folding fit that was presented in Giacomo's introduction to statistics. Basically, what we do is that we assume over a certain energy range that our spectrum, the distribution of events, is well described by some analytical function. It's typically a power law because we know from the cosmic rays that particles have a particle power law distribution, so they will produce power law photons. So it's a power law or some variation of a power law. For example, here I have a log parabola, which is basically, as you can see, a power law whose spectral index changes with energy. Okay, so it will appear like a smooth function. As you can see, it's a function of energy, and then we have some parameters that we want to estimate, right? For example, the amplitude, this reference energy, the steepness of the power law indicated by the index. And this is basically how we perform measurement. For example, here you can see a measurement of the Crab Nebula spectrum by magic. And as you can see, what we did is basically assume a log parabola and fit it to the whole spectrum. And here you can see the same by Hess, basically different. I think one is a power law with a cutoff, but basically what we do is we assume all the spectrum is described by some analytical function, okay? Let's examine the analytical spectra available in gamma pi, and here I show a power law spectral model and a log parabola spectral model, okay? As I said before, power law, log parabola is basically a power law with changing index, with changing steepness, okay? Okay, but what I want to measure is flux versus energy, precisely differential flux, okay, versus energy. So something that has units of TeV minus 1 because it's differential in energy, and then the typical flux units, no? Centimeters minus 2, second minus 1. How do I do that when I have counts in the detector, when the measurement, the actual measurement that I have is counts in a detector? How do I connect some absolute physical quantities, flux, no, with the, we might say, relative physical quantity, relative because that's the measure of counts in my particular detector at that particular time under those particular conditions, atmospheric or observational conditions. How do I connect the two? Through the IRF, right? The IRF allow me to go from flux to counts. Okay, I have an effective area, so I can eliminate the centimeters minus 2 value, and I have an observation time, okay? And basically, that's what this formula does. Basically, using the IRF, AF here represents the effective area, ME prime E represents the migration matrix, prime quantities are measured quantities, and what you can do is, given a set of parameters of your model, multiply the assumed spectrum by the response integrated in estimated and true energy, and then basically you get some predicted counts. And this, you can feed this estimated number of counts can become, if you remember, when we define the likelihood, we have some average, expected number of signal and background count. Through the folding, we can get basically this number, the expected number of signal counts, okay? So I make an assumption of the spectrum, and I get an estimated number of expected counts, okay? And then I plug them in my likelihood formula. And B is treated as a nuisance parameter. We will not enter in the details, but just, let's say B is optimized in a slightly different way. Okay, so let's actually do it. So it is usually proper to fit an energy range in which you know that you have a proper response of the system. So typically, let's say above 80 GeV for this type of observation, and then it's optimal not to include empty bin in your fit. So if you see here, I used some energy range that reflects this. So I want to fit the counts between 80 GeV and basically 20 TeV, because above 20 TeV, I basically don't have counts, or I have one count. Yeah, basically I don't have count, as you can see, okay? So you have to use a reasonable fitting range, okay? And then I will assign, basically I will define a spectral model, the log parabola, and I will assign it to the data sets. Okay, so data sets is the list of this reduced data here. Okay, basically I have a list of this type of data, binned data, basically, and I will assign a model to this data. And so basically what I can do now with the function plot XS, per each data set, I can plot this predicted signal counts, okay? So dataset 1. So what I'm doing is I'm saying to the routines, basically, this is the power law this is the model that I define. It's a parabola in this case. I will plot it here, spectral model. Okay, what I'm saying is take this flux model, pass it through the IRF, through the integral that I defined here, so multiply it by the effective area and the migration matrix and integrate it, and then tell me how many counts per energy bin I will get with this model. Okay, so the orange is, let's make this one orange as well. So the orange counts are basically the log parabola passed through the response of the system, okay? If the flux was described by this function, and I would pass this flux through the IRF, that's the number of counts that I would obtain. Is this a good description of the counts that I am observing? No, not at all, right? I'm missing by an order of magnitude the actual counts that I'm observing, right? So, and we can check also the statistics, right? The likelihood, basically the value of the 2 log of the likelihood. So let's try to do something. Let's increase the flux of this model, okay? Let's increase the amplitude parameter. Let's scale upwards this model. That's what I do here. So the value that I selected was 5 10 to the minus 12. Let's scale it upward. Let's use 5 10 to the minus 11. So let's scale it upwards of an order of magnitude. And then let's plot the excess again, okay? Is it clear what I've done? So I just scaled up this model. I've assigned it a new amplitude parameter. And as you can see, when I increase the flux and pass it through the IRF, I get a better description of the data. Maybe it's still not optimal, but it's much better than before. How can I quantify how better it is? Through the likelihood. So before, with the parameter 5 10 to the minus 12, I got 383 for the likelihood. And if I increase that parameter, I obtain 21. So big improvement in that. Remember that this is minus 2, the log of the likelihood. So we are minimizing, sorry. We are minimizing this parameter. Is it clear more or less how does this work? So basically this is the fitting algorithm. I have certain parameter of my model, and if I change them, the likelihood value will change, and my algorithm will stop. Let's say will find the parameters of the spectrum that convolved with the IRF will give me the counts that better represent the counts that I actually measured. Any question? This is really an important point, and as you can imagine, the algorithm is changing several values at once. So for example, if we change also alpha, we get a different stat sum, not so different, but a different stat sum value. And if we use some reasonably large value, the stat will worsen. No. Did not? Alpha 5. Let's change this, for example, to 7. Yeah, I'm starting to overshoot the counts, as you can see. So you can see also which parameter has more impact. So if I change the amplitude, sorry, that was the problem, alpha. So these are values pretty close to the optimal values. And if I start to, and the statistic is 30, and if I start to mess around with them, if I start to change them, the statistic will worsen. You see, just changing the index from 2.16 to 3 really worsened my likelihood. Is this clear? So basically the algorithm will scan basically a space of alpha and amplitude parameters and will find those that provide the minimum likelihood. So Guilherme, let's reply to the question, asked why the number of pins in true energy is different. It is basically, Guilherme, for this integral. Basically, to compute counts from differential flux, you need to integrate over true energies, okay? You are integrating basically over the axis of the IRF. Remember, all IRF are functions of true energy because we build them from the Monte Carlo. So when we are doing forward folding, it is recommended to use a larger binning in true energy than in estimated energy because we are integrating in this dimension. And for estimated energy, we are just integrating over a bin because we just want to know the counts in this bin, okay? So imagine that here there is another energy axis, the true energy axis, and this is the estimated energy axis, and we want to have that axis finer to integrate over it. Is it clear? Does this address the question? Okay, perfect. Yeah. So better to have a denser true energy axis because we have to integrate over all that axis, while to estimate the counts in a single bin, we just need to integrate over single estimated energy bin. Okay, so we got more or less how the optimization algorithm works. So let us let gamma pi do this optimization. This is what the fit function does. So it will run, and basically it will estimate for all the data set, taking into account all the distributional counts in all the data set, what is the model that best reproduce all the data set. Okay. Taking some time to fit. Okay. Okay, so these are the optimal parameters. We fixed the reference, otherwise we have too many parameters and the model is degenerate, meaning that the algorithm cannot distinguish how the flux changes when it changes different parameters. So typically we fix this reference energy, E0, where is it? Typically we fix this value. And then, yeah, it basically gave us the optimal values of alpha, 2.5, and of beta, okay? And when I plot the same histogram now of the excesses, you can see that it reproduces quite well the excess that I observed. And this is valid through all the observation, right? It found the values of the analytical spectrum that best produce the counts in all the observation, let's say. Okay, any questions? Okay, it is common practice in high energy astrophysics to represent E squared d phi d, so the differential flux multiplied by E squared. I explained why this is the case in the tutorial. It's mostly because this is basically when you do this multiplication, you obtain, there is a typo here, sorry, the power emitted along the electromagnetic spectrum. And basically the other visual advantage that you have is something that has a power law -2, which is what we typically observe in cosmic ray, will appear flat in your log-log plotting, right? And here I compare the result that we got. Sorry, it should be magic, not LSD. This is the spectral model that we fitted compared with the previous result from magic and with a theoretical model that uses several multivalent data. So we got quite a good agreement with previous measurements, okay? What might be one limitation of this approach? One limitation might be that we are assuming that from 80 GeV to 20 TeV, we are assuming that the model that the flux has this smooth distribution, right? We are assuming that our flux is some smooth function, right? And this might not be the case. So what one typically does is to compute flux points. This is basically a flux measurement in different energy bin. It's the same process as before, but instead of fitting the spectrum using all the counts from 80 GeV to 20 TeV, we repeat the likely process bin per bin, and we get a flux measurement bin per bin. What you typically would do is also to fix the spectral index, okay? So you see basically bin by bin how your broadband fit scales, okay? And once you have this measurement, you also have some measurement of flux versus energy that you can pass, for example, to a theoretician if they want to do some modeling, let's say, right? It would be difficult to fit, let's say, doing a chi-square fit if you have a physical model of this measurement, right? You have basically because you are already performing some kind of fit, right? You have basically a single analytical function that represent your flux with some errors, right? But if someone else doesn't have access to the data like we do, they might have trouble in fitting any other model, right? So we have a flux points estimator in gamma pi that will do this. Basically, it will repeat the likelihood fit, but taking into account only the events in each energy bin separately and independently. So it will take the spectrum and readjust the amplitude only to the events in one energy bin. I think it will take some time to do it. Almost 10 minutes. Wow. Okay. To estimate the flux point, I guess, right, Tora? Just for that cell. Interesting. Okay, thanks, Fabio. Remove the selection optional all for faster processing. And actually, we can also do the later exercise of stacking the observation. Okay, and Fabio suggests also to use, you have basically an option to use more than one job to run the flux points estimation. Okay, I think we can start to go to the following exercise, and then we come back and we comment on the flux points estimation. Basically, what you have now, I will pause it for a second. Okay, so in the first two notebooks, we consider the crab because it's a bright and steady emitter, so it's easy to use it as a reference source. And the most important point is that we can stack the data. Now, when we are not interested in, let's say, observation by observation variations, 20 minutes variation, given the observation that we take, if we are not interested in a fine time scale, let's say, we can stack all the observation together and perform our statistical estimation. But what happens when we have a source whose flux changes a lot as a function of time? This is what we'll do in this notebook. So we do the data reduction as before. We use the data store to read all this Markarian 421 data. Markarian 421 is one of the closest and brightest active galactic nuclei with a jet. And I'm interested only, I have data over more than a week, but I'm interested only in the 10 days between the 10th and the 20th of April. So I will use this observation select time function to basically pick up only the observation between the 10th and the 20th of April. Okay. So times goes from noon to noon because we observe at night. So if we want to encompass the whole night, it's better to use, let's say a time interval that starts at and ends at noon. Okay, so that the observation night falls largely within this interval, right? The interval is larger than the actual observation period. Here is basically the same process that we did before. So coordinates of the source, the two energy axes, we create the data set and we fill it. We use it 3 off regions, okay? So exactly the same as we did for the crop. I think it will take a minute because there are 186 observations. In the meanwhile, I'll start to describe what is a light curve. A light curve is a measure basically of the intensity of a source as a function of time. There are different ways of measuring the intensity or the brightness of a source in gamma ray astronomy, in astronomy in general. And how do we do it in gamma ray astronomy? We basically take the flux, the photon flux, okay? But if you remember, to describe the spectrum, we use the differential flux, right? A flux divided by the differential in energy. So what we do is basically we integrate this flux above a certain threshold. That way we can go from a differential to an integral flux, right? Still reducing the data. And basically, we will use a process that is very similar to that of the flux point estimator. Remember when we used the flux point estimator, what gamma pi did under the hood was basically take the differential spectrum and fit it only to a given energy bins, okay? So I fit it to the events only that fall within a certain energy bin. The light curve estimator does the same, but for events that fall within a given time bin, okay? Because we want to estimate flux versus time. So it will basically perform the likelihood fit bin by bin in time, okay? So we basically define some predefined time bin for our light curve, and the light curve estimator will do this process. But we need some starting point, right? Because when we estimated the flux points, we passed the flux that we the broadband flux, right? The best fit to the entire energy range, right? So we said start from this log parabola and adjust it in each energy bin. So from which spectrum do I have to start in this case? Well, we can start from a spectrum that describes the observation altogether. So what I'll do is I will actually stack the observation, but just to get some spectrum that is an average description of the source, okay? So we need a starting point to estimate the flux bin by bin, time bin by time bin. Let's just stack the observation together and let's use the spectrum that describes all the observation, this average spectrum, as a starting point, okay? So this is what I'm doing here. So I have now 2 data sets. One that is called datasets that contains all the observation individually, and then a stacked dataset that contains all the observation together. And then I basically repeat the fitting procedure as before. This is the value that they indicate in the paper. This is a spectrum that decently represents all the observation together. It's a log parabola with a 2.14 index and 0.45 beta, the second parameter. And what we get is similar. I have here, yeah, we get 2.16 and 0.37 instead of 0.45. So quite close to the paper. Here, I just did a minor conversion because the logarithm in the magic paper is a logarithm in base 10, and the logarithm in gamma pi log parabola is a logarithm in base natural logarithm, let's say base e, okay? Take all the data together, obtain some average spectrum, and now we perform the light curve estimation, okay? So as before, we need some energy edges. We want to estimate the light curve in a certain energy range, and typically we will integrate above a certain energy. Let's integrate above 1 TeV, for example. And then we want, when we perform the flux estimation before, we just changed the amplitude, right? We want to do the same in this case. So we froze both the alpha and beta parameter. We want to adjust in each time being just the amplitude of the flux. Then we define this light curve estimator. It's very similar to the flux point estimator, but in this case, we should define some time binning, okay? If we don't specify any time bin, it will just produce a time bin per each of the dataset, per each of the observations. So in this case, it will, if I don't specify anything and I run the light curve estimation, it will consider time bins that encompass exactly each of the observations in the dataset, okay? So we will have some scattered night, each of them has 20 minutes duration, which is basically the duration of the observation in a single run for magic. Any questions so far? So sorry if I'm repetitive, but exactly the same process as before, but we are readjusting time bin by time bin rather than energy bin by energy bin. Okay, it did it. Let's plot the light curve. Here we see the integral flux above 1 TeV as a function of time, okay? And you can see the different days. As I said, if we don't specify any time binning, it will just produce one flux measurement per each observation. So each of these points is one of the observation, is 20 minutes of data taking in a given night. And you can see here the different night, 11 of April 2013, 14 of April 2013, etc., etc. It is common practice to represent time in modifying Julian date in astronomy to have a continuous count of time. It's basically a number of days from a certain reference date, okay? And that's what we do here, okay? And yeah, I just changed the time format parameter of the plot function of the light curve. Okay, as an exercise, you can do it as a homework, or we can go back to it later if we have more time. I just ask you to compute the light curve assuming a power law spectral model, because here, as a spectral model for this readjustment, we use the log parabola, basically the log parabola that best describes the data in average. Okay, I wanted to do something more interesting, which is play with the time binning, right? Because maybe we want to study the variation of the source over a predefined energy scale, because we have some physics in mind. For example, we are thinking to some physical process that should manifest over daily time scale or over minutes time scale. So perhaps we want to adjust the flux measurement to larger or smaller binnings, no? And what I suggest here is to do daily binning, okay? So here, each day I have a 20 minutes measurement, flux measurement, which is each of the observation. Let's define now time bins to be the width of a day, okay? And we do the light curve estimator as before, but we pass it now to time intervals, these new time intervals. This is basically noon to noon of each of the 10 days of the observation, okay? Remember, noon to noon, because typically with magic, we observe from 7 in the evening, 8 to 6 in the morning, depending on the season. So with a very large bin noon to noon, we are sure that we encompass all the measurement, okay? Okay, as you see, it's really faster than before, because now it has to perform the adjustment just in 10 time bins. Before it was 186 time bins, one per each observation. And we can compare the two. So I have what I call the run-wise light curve. So a light curve for which the flux was estimating in each observational run, and a daily light curve. So a light curve for which the flux was estimated in each day. And if you wish, you can see that the results are consistent, because more or less the daily flux measurement is some type of average of the nightly measurement, okay? Why we will do that? For example, we want to communicate in our paper how the flux changed day by day, or we are studying some physical processes whose variation has a time scale of a day, okay? What is very interesting is also to plot the spectral parameters versus time. So for when we estimated the integral flux, we freeze all the parameters except the amplitude. And this type of light curve only shows us the overall flux variation, right? I'm just measuring how much the integral flux changes over time. But perhaps I want to measure, for example, how the stiffness of my spectrum changes versus time, because maybe I'm studying some other physical process that modifies the slope of my photon distribution, right? So that's what I will do here. Basically, I create a list of spectral models, so a series of power laws, okay? And then I will select a sub-dataset for each day, okay? So I will do the select time per each daily time interval, basically, and then I perform the spectral fit of each day, okay? So basically, I take in parallel one daily time interval and one spectral model, okay? And I run the fit. So at the end, I get a list of spectral parameters per each day, okay? So I should get 10 power law spectra adjusted to the data set in each of the day. One, two, three, four, five, six, 10, 8, 9. I think it's done. Yes. And now we can make this very interesting plot of not only we know the integral flux, how did it change in each day, right? This is the measurement that we did before with the light curve estimator. But now we know also how the spectral index changed day by day, right? What can we do with this information? We can produce what is called harder when brighter plot. It's a behavior that certain sources show, especially Blazar, like Markarian 421. And what you see is typically that when the spectrum becomes harder, so when your spectrum becomes more flat, the index goes closer to 2, basically the brightness of the source increase, okay? This type of behavior gives us relevant information about acceleration mechanism of the sources and radiation. So there are certain processes for which your spectrum will become higher in flux and harder at the same time, right? And then basically what I do is a scatter plot of the two. And if the two are correlated, so if you see your spectral index diminishing versus your integral flux, then you're observing a harder when brighter behavior. And to a certain extent, we are observing that here, okay? So I just wanted to give you, let's say, a more different way of studying the temporal variation, okay? Not just computing the integral flux, but for example, also studying how the parameters change and relate that to something physical, okay? Okay, so our source to a certain extent is showing this harder when brighter behavior because the integral flux correlates with the hardening of the spectral index. What else can we study? For example, we can go in the other direction, right? We wanted to measure daily how the flux changes, but maybe we are studying some physical process or we are doing some study with new physics like Lorentz invariance violation, where we want to study really small time intervals, right? So for example, I would like to study in the day in which I had the higher flux, which I think is the 10th of April. No, the 13th of April is the day in which my source peaked with its flux. I want to study if there are variations shorter than the observation, okay? Here I have 20 minutes time beams. For example, I'm interested to check if I have 5 minutes or 10 minutes significant variations of time. So let's do that here. So let's basically just consider the flare day, which is the 13th of April. And then I just compute the runwise light curve just for this day. And then I want to make now 5 minutes interval, okay? There is a warning here because if you have time beams that are larger than the observation time, then there is no problem for gamma pi. It will automatically cluster together and stack basically the observation within this time bin. But if your time bin is shorter than the observation time, in this case, 5-minute intervals, when you have 20 minutes observation, you have to cut the observation as well, okay? So time bins larger than the dataset, gamma pi will stack, but shorter time bins, you need to cut your observation in 4 in this case, okay? So that's what we do here. We define 5 minutes duration, then I just make a list of 5-minute intervals, and I do observation dot select time of this new list of time intervals. So I have a list of time intervals, 5 minutes each. I just take the whole observation and I cut them in these 5-minute intervals. And then of course, after I do that, I have to produce data set from this cut or cutted observation, no? And that's what I do in the following cell. I call them short data sets because they're shorter than the standard data set from which I started. And then I perform again the background estimation as before. So the dataset maker, the background maker, and blah, blah, blah. Any questions so far? It's taking some time. I think it's mostly due to the cutting of the observations. How small can the time bins be? Very good question. I think this depends on the physics that you want to study and especially on the statistics that you have. If you have a source that is very bright, then I don't know, if it's super bright flare from an AGN, maybe you can go down to 5 minutes spinning or 2 minutes spinning, as long as you have sufficient statistics in each spin. But of course, if you have a source that is not bright, then if you cut the bins too small, and then you will end up having basically upper limits in all the energy bins. So it's a balance between, let's say, the physics that you want to do, but especially from the depending on the statistics that you have. If the question was technical, I don't think there is any technical limitation from the gamma pi side. Of course, I don't know exactly how the IRF are treated when you no technical cut from gamma pi. I think it will start to mess up if you make too small time intervals or not. I don't know. Fabio, do you know by chance how the IRF are treated when you cut the observation in smaller times? Are they just scaled by the different shortest time bins? Okay. I don't know. I would say that maybe you have some technical problem if you start to go very low, and I don't see the point, let's say, of making 20 seconds time bins, for example. Okay, so we got the data set, a list of data set that is now 5 minutes long. And then what we do, we run the light curve estimator on this new data set. Okay. I think it was supposed to print how many data set we have. No. It's 98. So we have 98 time beans now. For example, what we will see in a minute when the light curve estimation finish is that we're not really adding that much information in this case by reducing by shortening the time beans. Yeah, you can see here in blue the run-wise light curve. So the light curve computed in each observational run, and as you can see, these were 15 minutes run actually, and as you can see that per each run we have 3 5 minutes interval. You see? Yeah, so that's it. In this case, yeah, I don't know. I wouldn't say that we are learning much more. No, I don't think that if we adjust some kind of function to this to the 5-minute binning light curve, we will get different results that adjusting the function to the run-wise light curve. But in some cases where you have extreme flux variation, perhaps it might be interesting to use smaller time bits. Okay. And then as a last step, let's actually fit this light curve, right? Maybe we have some physical model or we just want to fit it with analytical model, the time variation. So I defined a flux point data set with the light curve data with a run-wise light curve. I don't care fitting the 5-minute light curve. It was just an example. And as we can see, we don't learn anything new. So I transform this in a flux point data set. A flux point for gamma pi can be both in energy or in time beans, okay? Then I define a time and a spectral model. So for a spectral model, in this case, I use a constant, right? I'm just fitting in an energy bin. I'm just estimating the integral flux between 1 TeV and 100 TeV. I don't remember, so I don't need to adjust this. This is a constant for me, right? But from the time side, yes. And I start with a linear temporal model. So I plot here, I think, no, I don't do any plot. So basically, I define a sky model before, if you remember, when we defined the sky model for the crab, for example, we just specified the spectral model. And now I specify also a temporal model, right? So now in this model, I just have a constant for flux, and I want to study how this flux changes in time, which is what I do. The fit was performed, and as you can see, this is more or less the line that would decently fit our data. Okay, and then as an example, I can see here that there is a bump in the flux, right? Or perhaps I would like to add a cushion over this line, right? Maybe my flux is linearly increasing in time, and then at 2 a.m. in the night, there is some burst, another burst of flux, okay, that maybe I can describe with a cushion. So here, what I did was to define a custom temporal model. It's called Gaussian plus linear. The good thing of gamma pi is that you can also define your own temporal model and spectral model and spatial model as well. So basically what you have to do is to define a list of parameters, so alpha and beta, that would be the parameters of the line, the coefficient and the intercept, let's say, and then amplitude and sigma for the Gaussian, okay? And then you just have to define the list of parameters and, well, some reference time, and then some evaluate function, okay, that then gamma pi will read. I assign some of this value, okay, and then what I do is I create a new sky model with a spectral model that is always a constant and with this Gauss line temporal model. I assign it to the data set and I just plot it, okay? I'm not fitting here, just plotting. So I assign to the data set, each data set has this dot models attribute, as we saw before, where you can assign a model, okay? So this is the initial model. Now let it fit. Okay, it worked. And let's examine the result. Yeah. Okay, so we got some model that more or less describes our data. Okay. So that's what I wanted to show you for the time variation. So not only just to compute the flux versus time, what we did and what we do in a normal light curve, but also how to study how the spectral parameters change with time. That might be interesting, and also how to fit your light curves, because maybe you have some simple model that can produce a simple, let's say, electromagnetic emission model that changes in time, and you want to see if it represents your data well. Okay, I plan to finish at 1, so we have some time. We can go back to the exercise 3.1. That was to estimate, I think, the light curve assuming a power law spectral model. So we can try to do this. Let's use the round-wise light curve, okay? So let's try to see what difference does it make if we are assuming a log parabola and we are adjusting the amplitude of the log parabola run by run. And if instead we use a power law and we are adjusting the amplitude of the power law run by run, okay? I think this one will take some time, so let's try to do it. Let me know if you have questions. I will just wait a bit and then I'll try to do it as well.